All right, what I want to talk about today is the derivative. This is a big, a healthy big step for us. The derivative. Something that you know well and love from calculus. We're going to talk about the derivative. We are not going to do the derivative over and over again like you do in a calculus class, because you all know how to do that already. But there are some things to discuss sort of at a more sophisticated level perhaps than we did in your calculus class. But anyway, let's just get with the definitions. Like, for the most part, stuff about the derivative tends to be not so complicated. If you feel like this course may be characterized by taking things that you thought were simple in calculus class and like making them much more complicated. But actually, the derivative, we're not really going to do that sort of thing with the derivative. So I hope you're not worried about talking about the derivative in this class. Anyway, let's just do the definition here. So if f is a function, let's just say r to r, although really the domain doesn't have to be all of r, but is a function, and c is in the domain of r, of f, sorry. C is a point in the domain of the function. Then what we're talking about is the derivative of f at c. The derivative of f at c is f prime of c equals, and now I'm just going to write like the ordinary definition from of the derivative from calculus. You want baked goods?
Sure.
I got baked goods made with real pumpkins.
Oh my gosh. Thank you so much. Thank you. That's so nice.
We are just going to write the definition that you use in calculus with a limit. Now, there's actually two ways that this is often done in a calculus setting, and I don't know if this is the way that you like, but this is the way that it's defined in our book. Lim x goes to c, f of x minus f of c over x minus c. I think if you take the calculus class here, we usually don't use this definition. This is equivalent to this is a little more common in my experience in like a typical calculus textbook or something. Those two definitions are equivalent, or sometimes this one is written with a delta x instead of a h, but whatever. This is the one that we are going to use in this class. That's the definition of the derivative. Limit as x approaches c, f of x minus f of c over x minus c. And everybody knows this represents the slope of the graph of the function at the point x equals c. Although we, in this class, you can do this definition even for an insane function. It doesn't have to be a function which looks like any kind of ordinary function with a typical looking graph. So you can still think of this as the slope of the graph, but it's not always that clear, because we are not always going to talk about it in terms of ordinary looking functions. All right, but the good news is, like, you don't really have to do this using the epsilons. I mean, it's the derivative is defined as a limit of something. So if you're lucky, you can find this limit by using the limit tricks rather than going hardcore with the epsilons every time. All right, and let me just say one last bit of terminology. This is the definition of the derivative at a point, and if this exists, f prime of c exists. Of course, it is a limit of something, so it might not exist because sometimes limits do not exist. But if f prime of c exists, we say f is differentiable at c. All right? That means that the derivative exists. differentiable at C? Welcome. I got baked goods. Are you interested? Right here. Made with real pumpkin.
Thank you so much.
Mm-hmm. All right. That's what it means to be differentiable. It means the derivative exists. Let's do some examples. How about just one example, maybe? This is the time in calculus class where you would spend the next like 3 weeks doing hundreds of examples, but we're going to do one or two, and that'll do it, because you've already seen all the hundreds of examples. How about f of x equals x to the n is differentiable at any c, right? X to the n is differentiable at any point. This is what I would like to demonstrate. So we just got to use the definition and show that that limit exists. So the definition is f prime of c is, so this you just have to remember. I don't know if this is the same definition used in a calculus class, but this is the definition of the derivative. F of x minus f of c over x minus c. The limit of that, all right? It is our job to show that this limit exists. That's all you got to do. We can do this by trying to simplify. I can first of all simplify by plugging in for the f. This would say lim x goes to c, x to the n minus c to the n. Remember, f means nth power. So f of x is x to the n. F of c is c to the n divided by x minus c. Right? And now, can we simplify this at all? The answer is yes, if you remember some somewhat obscure trick. There is a thing, this thing, x to the n minus c to the n. You know, if the n was a 2, if it was this, then you know how to factor that, right? It'd be x minus c times x plus c. If it was this, you may have forgotten, but this at least you know there is some weird formula for that. You use it on the homework. We use it in class a couple times. In general, actually, there is a formula for x to the n minus c to the n. Would you mind if I just tell you? You could look this up somewhere if you like. Anyone actually know this formula? It factors, this works regardless of what the n is. It factors as this, x minus c, and then the other part is x to the n minus 1 plus c, x to the n minus 2 plus c squared, x to the n minus 3, etc. And then all the way down, as you go through this sum here, the power on x decreases each time while the power on c increases each time. The last term looks like c to the n minus 1 times no x's, right? It's like that. And I think I left something out of this formula. No, it's fine. Okay? That's what it is. So this I'm going to use to factor x to the n minus c to the n in this numerator here. And then actually we'll be able to cancel x minus c. So f prime of c is lim x goes to c. What I had before was x to the n minus c to the n. I will put this business, that formula that I just wrote, plugging in for x to the n minus c to the n. X to the n minus 1 plus c, x to the n minus 2 plus blah, blah, blah. C to the n minus 1 all over x minus c. And now some nice things will happen. We can cancel the x minus c's, of course. And then I just have all of that stuff lim as x goes to c. All right. X to the n minus 1 plus c x to the n minus 2 plus blah, blah, blah. C x to the n minus, no, just c to n minus 1. All right. And how can I take the limit as x approaches c here? Yeah.
Plug in C.
Yeah, just plug in c for x. you should worry like if there's a 0 in a denominator or something, some funny business like that, but there's no funny business here, right? It's just powers of x. Since powers of x are continuous functions, you can do the limit by just plugging in the limit value, which is c. So I am going to plug c for x wherever I see it. It now will, well, I'm doing the lim, so don't write lim anymore. Plug in c instead of x. C to the n minus 1 plus c times c to the n minus 2 plus c to the n minus 1. Oops. Minus 1. All right. Can we simplify this at all? I have c, I guess c to the n minus 1 is going to stay like it is. What can I do with c times c to the n minus 2? It is c to the n minus 1. Yeah, you add the exponents, right? Plus, what about the next one? The next one would have been c squared times c to the n minus 3. Again, you add the exponents, you get c to the n minus 1. Actually, all of these equal c to the n minus 1. So we can add them all up. How many of them are there? I think there are n of them if you are careful about how you count these up. Here we begin with x to the power n minus 1 going all the way down to the x to the power 0, and so there are a total of n of them. So this is n times c to the n minus 1. And that's what the limit is, all right? And so the limit, in particular, the limit exists. So f prime of c equals n times c to the n minus 1. So the limit exists because that's what it is. It equals n times c to the n minus 1. So f is differentiable. All right, at c. Welcome. We got baked goods. They're at your seat, but you can't have them all. Take one. Even though you're late, you should only get 3/4 of one. Because you missed 1/4 of the class. All right, the limit exists. So f is differentiable. In fact, if you follow through what we said here, f prime of c is n times c to the n minus 1. If you write this using x's, it says n times x to the n minus 1, which of course is everybody's favorite formula for the derivative, right? The derivative of x to the power n is that, n times x to the power n minus 1. So everything works out just the way that we would expect, all right? And like I said before, you usually will not have to get into the epsilons business, right? We just use sort of simple tricks with the limit and everything worked out. Although in theory, in order to calculate those limits, you might have to use the epsilons in a bad situation. All right. How about showing that a function is not differentiable? This sometimes does require the technicalities that we are now accustomed to. So how about a non-differentiable function? Here's everybody's favorite example of a continuous function that is not differentiable, I think, is the absolute value function. It is continuous, but not differentiable at 0 because the slope is messed up at 0. All right. So here, f of x equals absolute value x is not differentiable at x equals 0. Let's see, can we demonstrate that? We don't really need the epsilons, but we are going to have to discuss specifically something about the limit not existing. So let's see if we can make that happen. F prime of 0, just using the definition of the derivative, it would be this. Lim x goes to, remember it usually says lim x goes to c, but c in this example is 0, so it's going to be lim x goes to 0. F of x minus f of c would be that. I'm using c equals 0 in the definition of the derivative. Some of this we can simplify, but I want to try to compute the limit. Actually, more specifically, I want to show that the limit does not exist. But what can simplify? Just the x minus 0 on the bottom is just x. And f means absolute value in this example. So this is really absolute value x minus absolute value 0. That's just 0. Would you mind if I just leave that part out? This is what we're talking about here, right? Absolute value x divided by x. And what is that limit? Actually, this is kind of similar to something you did on the homework maybe 1 time ago. Which had like 7/4 in it. Remember that one with the 7/4? Yeah. I mean, it was a similar kind of absolute value of something divided by the same thing again. Maybe you don't remember that. I found the 7/4 to be memorable. What about that? Absolute value x divided by x. I think the way, if you did that homework problem correctly, you thought about this, realized this is a fraction where basically the numerator and the denominator are the same, it's just they might have different signs as one another. That means this fraction is either going to, its value will either be +1 or -1, right? And in particular, you can say what this is right there is really this function. It's 1 if x is greater than 0, and -1 if x is less than 0, right? That's what that part of it is. And if x equals 0, then this is not defined. But it doesn't matter because I'm taking the lim as x goes to 0, so x equaling 0 is not relevant. It's just the lim as x approaches 0. All right? Anybody think you can show that that limit does not exist? This we can do. This would have been a nice question on the test, perhaps. Easy question. How would you show that this limit does not exist? An idea? Yeah, how about 2 sequences which both approach the same, the sequences approach the same value, but the when you plug them into the function, it approaches 2 different values. You got 2 sequences in mind? Yeah, they should be 2 sequences which approach 0, one being positive and the other being negative. That's how you'll get the 2 different answers. So we're going to, let me just, as a little preamble, we'll show this limit does not exist. And we have to do this using sequences. That's the way that we always show limits do not exist. With sequences. So I'm going to say let xn be 1 over n, like he said, and yn be -1 over n. All right? Then these both approach 0. But when I plug them into the function, they don't both approach the same value, right? But f, now it's not actually f, it's what I'm plugging into is not what we called f up here. It's this, right? This is the function whose limit I'm trying to show does not exist. So don't write f here, but what we're showing really is this. Absolute value xn over xn. This approaches 1. Actually, it equals 1 every time because the xn's are positive. And the same with y's approaches -1. In fact, it equals 1 every time. All right. And so, since we had two sequences with the same limit, but when we plug them in, we get 2 different limits, that means that this limit does not exist. So lim x goes to 0, absolute value x over x does not exist. All right, this is how you show something is not differentiable. You've got to use sequences. Okay, how about, here's another fun example. That was a fairly ordinary, perhaps, example. How about this one? X sine of 1 over x, or 0. So this is if x is not 0, 0 if x equals 0. This is a cute function that we have talked about once before, at least once before. just the sine of 1 over x is the one where it looks like a sine, but the oscillations increase like crazy near the origin. And then multiplying that by x also causes it to have sort of a triangular shape to it rather than a flat shape, which just the sine part would have. Anyway, it looks like this. It sort of has kind of diagonal asymptotes like this, and it goes like that and like that. All right, roughly like that. Look at that, I put a little curly Q. Of course, that's not what it does. That's not a function, but you get the idea. All right, this is x times sine of 1 over x. It is, and then, of course, the first formula is not defined when x is 0, but you can plug in the point in the middle, and it's going to be continuous because of the way it goes in like that. All right, so this one is continuous. This we actually showed. This is continuous. At 0, at x equals 0. It's continuous everywhere actually, but 0 is the interesting point of this function. This is continuous at x equals 0. My question to you, is it differentiable at x equals 0? It also is differentiable at all the other points, kind of, just because it makes a nice smooth curve at all the other points. But what about right in the middle there? Is it differentiable? That's what I want to talk about. Is it differentiable? Let's see if we can work this out. So we use the definition of the derivative. Let's try it out. I'm trying to talk about f prime of 0, right? So this would be lim x goes, maybe I'll just write it first with the c's, but I'm going to use c equals 0, right? But this is just the memorized definition, and now we plug in 0 for c, f of x minus f of c, which is f of 0, divided by x minus 0, all right? And now plug in, what is f of 0? What is f of x? Now f of x, unfortunately, has this weird thing in two pieces, but actually, if I'm considering this limit when x goes to 0, remember this limit specifically, you do not have to consider when x actually equals 0. All that matters for this limit is all the other points. And so, actually, when I want to, for the sake of plugging into this limit, I can just use the first formula. We don't have to worry about the two pieces anymore, because all I care about is when x is not actually equal to 0. So here, this can be x sine 1 over x is what we're talking about, minus, what is f of 0? It says very clearly in the function, it's just 0. So that f of 0 is 0, and then divided by x, right? We can simplify, cancel the x's. Okay, and what is that? The lim as x goes to 0 sine of 1 over x. Is it, your choices are 0, does not exist, 7/4? It's not that one. Yeah, this one does not exist. This specific example we have done before. One way to convince yourself it doesn't exist is you could just, the graph of sine 1 over x is this one. And on the other side too. Right, I'm asking what is the limit, like does this function approach any specific y value at the origin? And the answer is no, it doesn't. It approaches sort of all of these values at once. One way, if you wanted to prove this, which I don't really want to get into the details, look back in your notes. We did exactly this example. You can choose one sequence. You would have to do this using sequences, but you could choose, for instance, xn equals something like 1 over pi times n, or you could use 1 over like 2 pi n plus pi over 2 to get different values out of this every time. But anyway, I'm going to say this does not exist. All right, so the moral of the story, so this is another example of f is continuous at 0, but not differentiable at 0. Much like the absolute value function. Only this one is more interesting looking, I guess. It's weirder. F is continuous at 0, but not differentiable at 0. I don't mean this function here. This is not f. This is that. F is this one, right? Continuous at 0, but not differentiable. To me, this is not all that surprising, just because I feel like this oscillation is still going up and down like crazy as it approaches the origin. And that, to me, that insanity in the oscillation will cause it to not have a derivative, because the derivative measures the slope. And the slope, as you get close to the origin, is changing from positive to negative over and over again, like infinitely often, which suggests to me that the slope probably doesn't have a limit as you approach the origin. All right? One more example, and then maybe that'll do us for today. If you liked this example, you're really going to like this next one. If you didn't like this example, you're not going to like the next one. It's very similar, but it's a little bit different. X squared sine 1 over x and 0. So the only difference is the square there. X squared sine of 1 over x. All right. What's the graph of this one? Well, instead of multiplying by x, when I multiplied by x, that's what gave it these kind of slanty asymptotes. It'll look like that, only instead of these asymptotes, it has sort of parabola type asymptotes. So it's like that one, but sort of bigger maybe. Somehow. So it does this now. And same on this side. And again, we fill in the middle point, sort of where it goes. So this version, what's different about it is out here, it's even bigger, like how far up it goes and how far down it goes. And in the middle, it's actually sort of smaller than before, because the parabola is there. Rather than having sort of straight 45-degree angles, actually these parabolas kind of have like 0 angles as you go in there. So in this one, the oscillations actually, in some sense, the oscillations are smaller this time when you get close to the origin. So something actually slightly different is going on when you're close to the origin. But anyway, my question, as before, is f prime, well, what I mean is f differentiable at 0? All right, let's see if we can work this out. Let's try. So I go f prime of 0. Again, same business here. It's lim x goes to 0, f of x minus f of 0 over x minus 0. This, when I plug in, I get x squared sine 1 over x minus 0 over x minus 0. All right. Cancel the x's. Now, last time I canceled the x's and they went away entirely, but it's not so this time. I cancel the x's, and what remains is x. Sorry, I should still write the lim here. All right. So what this turned into was actually the limit of the function we were talking about last time, right? That's actually the limit of this one. And does this function have a limit as you approach 0? I would say, so we showed last time that it is not differentiable at the origin, but actually it is continuous. I mean, we said that before, right? So the limit of this function actually does exist, and you can tell it equals 0, right? The y value equals 0 here. So this one that limit actually equals 0. We did actually prove that in detail long ago, but I don't want to get into the details of that, all right? So the moral of the story is that function is differentiable at the origin when this one is not differentiable at the origin. It's a little strange. This one is differentiable at the origin. So f prime of 0 exists, right? It equals 0. So f is differentiable at 0. All right? One more thing that I want to say about this function, and then this is basically will do us for today. But this function here, actually, you can take the derivative of the whole function if you know the product rule. Would you mind if I use the product rule and the chain rule just for the sake of talking about this function here? So this function here, using the product and the chain rule, we're going to talk next time about the product and the chain rule. I hope you remember the product and the chain rule. So I will write again the definition is this. This is f of x. So I can just take the derivative using my standard calculus tricks. Although, did you know, I don't know if something we don't really talk about in a calculus class, but if you have a function defined in 2 pieces, can I just take the derivative of each piece? Is that? The answer is yes, you can. You should maybe worry about when the 2 pieces are meeting up, but basically the derivative is something which exists point by point. At each separate point, there's a derivative. And so the fact that the function exists on 2 separate pieces, it doesn't matter. All you're doing is taking the derivative at each point. You can just do the derivative of the 2 pieces separately. So the bottom piece will still be 0. Sorry, I wrote these cases backwards. The first case is when x is not 0. The second case is when x equals 0. So here, the bottom case is still 0. The top case, x squared sine of 1 over x. This is where I'm going to use the product rule. So would you, any product rule masters out there? A little review for the comprehensive exam? I hope you remember the product rule. It's the first part times the derivative of the second part plus the second part times the derivative of the first part. So this is the first part, x squared, times derivative of the second part would be cosine 1 over x. And I'm doing the chain rule here. The derivative times the derivative of the inside is negative 1 over x squared or something like that. And then that was the first half of the product rule. Now I go plus. The second half of the product rule would be the second function, sine of 1 over x, times the derivative of the first function, which is 2x. All right. That's that. There is some simplification here. Right over here, this x squared and this x to the minus 2 cancel because they are being multiplied there. So really what this is, just to simplify, this is negative cosine 1 over x plus 2x sine 1 over x, or 0. All right. And this function, you can draw the graph of this. It basically looks like, I'm going to scroll. It basically looks like this one again, x times sine of 1 over x. But it's 2x here, rather than just, it's that part with a 2 in front of it. And then also you add onto it a cosine, which makes it ends up looking the same, but it has a slightly different, actually it doesn't look the same because the cosine part is always between 0 and 1, whereas this part has that sort of V kind of shape. Anyway, I'll show you what the graph looks like. You can type this into your calculator if you like to see what the graph looks like. It looks something like, it's big out here, but in here, it's it doesn't shrink all the way down to a point because of this cosine part, oscillates between -1 and 1 near the origin. And so the oscillations aren't super big, but they're still fairly big, between 1 and -1, all right? And it has this special point, say in green, is like right there. So it has this insane oscillation near the origin, but right at the origin, it's just 1 point in the middle there, all right? What's interesting is that is not continuous at the origin, because you can find sequences of points, say, if you only approach along the tops of these, it'll approach 1, but the point at the origin is plugged in at 0. So what's interesting about this is, so f is differentiable at 0. You know, f prime of 0 exists. But this is a graph of f prime. And f prime of x is not continuous at 0. So f prime of 0 exists, but f prime is not continuous at 0. All right. F is differentiable, but the derivative is not continuous. Another something which that means that f double prime does not exist. So this is an example that shows sometimes you can have a function where you can take the derivative but only once. The second derivative doesn't exist because the function, after taking one derivative, it has this very weird structure near the origin. All right, and I think that will do us for today, if you don't mind leaving 10 minutes early before the break. Next time we're going to talk about the chain rule, the product rule, that kind of stuff. Yes?
What's the difference between that function and the other one? One of the other ones that are like similar? Is that one has like a single point, so it's differentiable? Kind of goes to 1 point versus like oscillating about that one.
This is differentiable. Yeah, it's kind of because the oscillations actually get really small as you approach the origin. Like the derivatives here all go to 0. Whereas here, the oscillations stay big, so the derivatives don't go to 0. It's weird. Take another one of these on your way out if you like.